So as a final lecture for this curve fitting section, what I want to do is basically demonstrate all these methods in Matlab. So we've talked about least square fits and how you might do that. What are the sort of mathematics behind creating a line fit or a parabolic fit, Gaussian exponential fit to data. And so we want to talk about how you might use that, implement that in Matlab. We also want to talk about polynomial fits and spline fits and just take a look at all the kind of varieties things you can do in Matlab. And so I'm going to basically generate a data set, an artificial data set, and we'll play around with it. The other thing we'll do right at the end is show you how you might do a nonlinear fit. What I mean by that is if you have a function and it's not a polynomial and it's not this nice exponential, what might you do to still get a good data fit? After all, it's an optimization problem, right? You're just trying to figure out how I do this best fit, minimize the error. And there's ways to do that. So let's go over to Matlab and let's start programming away. Which one should I look at, Will? All right, good. So let's start thinking about it. I want to start making a data set. Let me make up a data set here. Just to play with. It's a data set I got out of the notes, but I'm going to give you the x values. Here they are. 4.9, 5.3, 6.0, 6.7, and 7. And I'm going to give you some y values. The y values are they correspond to wherever these x values go. And the hard part of teaching this right now without a real live audience is if I make a mistake, there's nobody here to catch me. So hopefully I won't make any mistakes entering in my data here. 2, 6.9, 5.3. OK, so there's my x, y data. And let's go ahead and plot this. So I want to plot x versus y and see what I get out of this thing. OK, good. I didn't make a mistake. So first of all, there it is. I just made up some generic data. Big deal. It's just this plot here. But part of what we want to start looking at is when I have this data, what do I want to do with it? Now, the first thing you'll notice right away is when I just did this plot, it did a connect the dots between the points. In fact, to more clearly see this, you can just say, OK, how about we do the following? We'll draw with red circles and a line. So it's going to have red, actually, magenta is a little bit brighter. Magenta circles where the data actually is, plus a line. So if I run this thing, there you go. So now what you see there is the data points. And you can clearly see that essentially the default in Matlab is to just provide a linear interpolant between each points. That's what those lines are. OK. So part of our mission then is to start thinking about, well, what do we want to do beyond just a line fit? We might want to start taking this data and do these least square fits or do spline fits. And so let's think about how to do that, and let's start using some Matlab commands to do so. All right. So the first thing we're going to do is a polynomial fit. And amazingly, the command in Matlab is called Polyfit. OK, polynomial fit, Polyfit. And what you do is you give it the x, y values you have that you're going to try to fit it. Well, here are my x, y values. And you give it the degree of polynomial you want. And what this is going to return, let's call this, are the coefficients of the polynomial. Remember, my polynomial was p of nx. And so p coef is going to be these polynomials of this fit. So if I run this right now, what it's going to do, in fact, let me go ahead and make this a little shorter so we can see the command window over here. If I run this, what's going to come back is p coef. And what these are, remember, polynomial of degree 1 is a line. It's ax plus b. And the a and b are what need to be determined. And there they are, a and b. Those are the coefficients that come back. And what it effectively did is it went and solved that 2x2 system of equations that we had written down in class a couple times ago. So let's try to plot this. So what I want to do is say, now that I got these coefficients and I have this line, I can plot this line. So let me make a line to plot. So let's take xp are going to be my values. I'm going to plot it from 0, steps of 1, all the way to 7, because that's where the x values go from. And my solution now, yp, which is going to be this line, what works with Polyfit is the polyval command. The polyval command wants these coefficients to go in, and I say, take poly to polyval, use pcoef, which are my coefficients, and evaluate them at xp. So this is going to evaluate a line here. So polyval will evaluate whatever the coefficients are. Now the coefficients I'm getting out right now are a line, so it'll give me a line fit, and I'll draw these lines at these positions, at these specified xp locations. So the xp you can think of as your interpolation or extrapolation points. I can plot this thing anywhere. I've chosen to plot them from 0 in steps of 0.1 all the way to 7. These are my interpolation values, and I can specify anything I want. I'm going to specify this. Okay? Now I can plot xp, yp. But before I do that, let's do a hold on here so that I get both. So plot this. And let's plot it in black. All right, ready? Go. And there it is. So there you go. There's the data. There's my line fit to that data. Now you can see this data isn't necessarily looking a lot like a line, and so I might want to plot something else, like maybe a parabola through that data. And you can compare the parabola to the line fit pretty easily. So you can say, oh, look, you know what? Let's do this again. Let's run this command. So copy and paste is the simplest thing. But now let's fit it to a second degree polynomial. Let's call this pcoef2. And then yp2 will be polyval pcoef2, oops, at the xp points. And let's plot xp, yp, and then xp2, yp2, which is a parabolic fit. It's degree 2 polynomial that's coming through there. And we'll plot that in green. There you go. Oops. I must have mistyped something. Oh, sorry. I just want to plot it at xp, yp2. Sorry. Go. There it is. All right, so now we have more data on there. Let me blow this up a little bit. Now we have 3 plots. The black line is a line fit. The green is a parabolic fit to the data. And the magenta is your actual data. Now, of course, not only do you want to plot this, you might actually want to calculate your error. Remember, what this green line and black line are doing are minimizing your root mean square error. And if you remember what the root mean square error is, it is the difference from your data point down to your fit. Like say for the line, it's from here to here. You square that distance and you add it to all the squares of all the other distances. Then you divide by the total number of points, and then you take the square root. So let's go and calculate this error. Let's call error 1. Error 1 will be the line fit error. So how do we want to basically calculate that? Well, what we've got to do now then is evaluate the data at the actual data point. So in other words, if I go back through this piece of code here, I want to evaluate polyval. You see right here? That tells me where I want to evaluate the fit, right? Evaluate polyval using the coefficients I got previously, evaluated these points. So I want to replace these points, which are 0, 0.1 to 7, with the actual data points, with x. Same thing here. I want to evaluate this thing with the actual data points there. Okay? So all I've done is I've just changed the evaluation of this thing so that the y values for the line and the parabola are actually being evaluated directly at the data points. And I need that to evaluate an error. Excuse me. All right, so let's look at E1. And what we want to do here is just basically say, okay, so what I want to do is look at the difference between my fit, which is, let's say, YP, minus the actual data. That's the difference. And I want the absolute value of that. And I want to square it. Remember, put the dot there because it's component by component. And then once I square that, I have a new vector with the square of the difference, and I want to sum everything up. So the sum command sums all the components of that vector. And once I do that, I divide by the number of points. And the number of points, let's call it n. How do I get n? Well, one easy way to do it is to say n is the length of x. So that gives you the length of the x vector, which gives you basically the total number of points. And once I have that, you want to square root it. Square root. There's your error. So that's the error that I get for the line fit. And if I copy and paste this, call it E2, and put in here YP2, then I get now the error for the parabolic fit. So if I run this, okay, there's the error. So if I do a line fit, my error is 0.9841. And if I do a parabolic fit, my error is 0.54, almost half. So clearly the error is going down. By the way, every time you make the degree of polynomial bigger, your error will go down. And the reason is, remember, if you go to the limit that you have n points, or you have n plus 1 points, and you specify an nth degree polynomial, the polynomial will go through every single data point. Okay? So the fact of the matter is that if you actually specify, the error will go to 0 eventually. So you can't just look at this and say, hey, look, the parabola did better than the line. Of course it did. Every degree you add will make the error go down. Okay? So you can't say, oh, look, that line really is more like a parabola because the error's better. Well, that's not true. It's just the fact that you have a higher degree polynomial. All right, but that's how you would calculate this error. All right, so now let's try to get a little polynomial wiggle in there. Because now what we could do is say, hey, look, if you want to think about this, let's do a polynomial wiggle example, ypn. And we'll evaluate that in a minute. And let's go ahead and not worry about these errors for a second. Let's come back and evaluate these things at xp and xp. And now let's do this polynomial wiggle. P co f n is equal to polyfit x and y. And now, if I again do n is equal to the length of x, then the degree of polynomial I want in here is n minus 1. Okay, so that's going to be n minus 1 degree polynomial, which will go through all n points that I have. Okay, so presumably my error should be 0 coming out of here, and then I can evaluate this thing at these points and plot it. X, y, p, n, and let's plot that in blue. Okay, if I run that, oops, let's do, oh. Uh-oh. Oh, no, never mind. Oh, so I have to put xp there. We're back to xp. Sorry. There we go. Now if I run this, let's see, get it, boom. There we go, look at that. See that polynomial wiggle? So let's first of all blow this region up where we had it before. If we look more closely here at the data, if I zoom in over here, this was the data before. See, the magenta is the data, the black is the line fit, the green is the parabola fit, and you see the blue? By the way, look how well the blue does right in here. The blue does a great job tracking here. The blue does a very nice job tracking the data itself. In fact, it goes through every single data point, does a fantastic job. But look what happens on the ends, polynomial wiggle. Look at this giant oscillation that happens on this end and also on this end. So you see, there's the polynomial wiggle we were talking about. We have all this data, and it's trying to make all these turns in the data, and this is a result of all that. And so you can start seeing right away that you don't want to use a polynomial fit for a lot of data, because it's just going to give you a really bad result in this way. Okay, so now what we have there is the error. We have some error calculations. We have these nice plots. Let me take off this this piece here now. And we have these nice fits. And this is how you use the polyfit, polyval commands. Polyfit and polyval just go with each other very nicely. In fact, let me go ahead and shut this out now. Delete. And make sure, boom. Oop. And gone. Okay. So there we go. We got some nice curve fits there, and they do a very good job. So let's move on then to thinking about other interpolation routines, including splines. Okay. So one thing to think about is the spline that we did is very smooth. All it is a method for doing interpolation. So it does not do extrapolation. These curves here on the L2 fit do extrapolation, but splines only work with from the endpoints of the data in between. You can't extrapolate outside, but so you can do a good job interpolating. So let's talk about the interpolation command. And we'll go through some of this. So there's a command called interp1. And what interp1 is going to do is you say, how about the following? I'm going to do the following. I'm going to use interp1, so which is interpolate. Here's my data I'm going to interpolate, x and y values. And I want values at x of p, let's say. Remember, x of p is 0 and steps of 0.1 to 7. In other words, here's a whole bunch of points, and these points are not where my data points are, so I'm getting interpolated values at the x of p. And what I want out of here is my interpolated values, y int. So if I just do this command, and I plot now xp versus y int, let's see what we get. I don't know if you could see it, but in fact, let's do the following. Let's go ahead and just make this a magenta circles. So the data are the magenta circles right here, here, here. The black is a linear least square fit line. The green is the parabolic fit. And you see this blue? That's my interpolated data. So the interp1 in its generic way is exactly what is the default. It just basically does a connect the dots. Just draws a line in between things. However, interp has some nice fancy features. Help, interp1. And you'll see all this stuff comes up. So interp, it's an interpolation of a 1D function, essentially. And look at all this stuff. 1D interpolation. Table lookup. Okay. So you tell it the x and y values you have. You tell it where you want to put x values, and it'll give you the y values. And then here's some nice options. It gives you some methods. You can use interpolation by the nearest data point, a linear interpolation, which is the default. A linear interpolation, just draw the line. A spline, p-chip, cubic, v5 cubic. All kinds of things. So let's play around with some of these. Okay, so first of all, let's look at nearest. What does that mean? So let's go put in here nearest and see what happens with that. Check out that blue. So what happens is, what the nearest says is, you give me a point, and instead of drawing a line between 2 points, the way it's going to do interpolation is going to say, you give me that point, I will give you the value of the nearest data point. This is what this is doing. This is why it looks like a step. So in other words, right in here, all these points here are giving you the value of the nearest data point, which is this one right here. All the points in here, nearest data point, which is this one, nearest data point is this one, nearest data point is this one, and so forth. So that's what nearest does. So instead of actually trying to give you some average of the values or a spline, it just says, okay, you want a data point here? I'll give you the nearest data point value that I have. Okay? So that's what nearest does. Let's do spline. Oh, look at that. So this is why people love splines. You see that blue line? That is a spline. That gives you this beautifully smooth thing. And it's not a connect the dots. These are all cubics between each data point. And the cubics are constructed by basically making sure that the function goes through all the data points and that the first and second derivative match at every single data point. And that's why you get this very smooth appearance. Okay? So that's what the interp1 can do for you. I actually don't know what the other, I haven't looked at what the other spline things are. P-chip. I don't know. Let's look at P-chip, see what it does. These are even fancier techniques. P-chip, there it is. Gives you something a little bit different. And here's what I want to highlight to you on P-chip. You see this region up here? Let's zoom in on it. Let's look at this region versus the spline. See how that is kind of like that point, data point's kind of a maximum, and this is a minimum. If we look at what the spline did something a little bit different. So remember that point, the maximum was right on that point. Notice what the spline does. If we look up here, look what happened. The maximum is over here. So the spline, it's just, I think it's one of these smoothing functions. It's just that it has a slightly different algorithm for how to do the smoothing. Okay? So there you go. So you have splines. And by the way, you can also do this with the spline command. There is a spline command that says, okay, y spline is equal to, let's call it YSP for spline, is equal to spline x, y, xp. So you can just directly access the spline with that command. And so now you get YSP. Oop. Oh, sline, not sline. No. Spline. I can't even spell it now. Spline. Okay, there we go. All right. There. All right. So the spline command, you can see, there it is. You can either do interp1, spline as an option, or you can do spline directly, and that's going to give you a nice data fit. All right. So let's do a help spline. I want to show you another thing about spline. Spline, as I said, has some options about how you do the endpoints. And so you can also see here that spline takes you to p-chip, p-val, some of these other different kind of splines. There's also the spline toolbox. The spline toolbox in Matlab actually gives you a lot of functionality in terms of accessing different kinds of splines. Remember, the spline imposes two constraints. And so in this default, there's two constraints. Remember, we had 4n equations, 4n minus 2 unknowns. So we had to supply 2 extra constraints. And this one here, the spline built in has a certain set of constraints that you can play with if you have the spline toolbox. Okay, so that is a nice implementation. You can see we did splines, we did polyfits, I showed you the actual polynomial evaluation. And so, you know, you have a lot of options there to play around with. Now what I want to do is give you a different set of data. So let's clear all this out. And I'm going to give you something else here. And then we're going to do a nonlinear fit. -3, -2.2, -1.7, 5, geez, 1.3, minus 1.0, -0.7, 0.4, 2.5, 0.5, 0.07, 0.5, 0.3, 0.65, 1.1, 1.25, 1.8, 2.5. Okay, I have this data, and my y values are going to be -0.2, 0.1, 0.05, 0.2, 0.4, 1, 1.2, 1.4, 1.8, 2.2, 2.1, 1.6, 1.5, 1.1, 0.8, 0.3, -0.1, 0.2. Okay, I have x and y data. Let's plot it. There it is. Kind of looks like a little witch's hat. Okay, in fact, I want to plot this just the dots. So black circles, and we'll just have this. So now, in this case here, part of the reason I bring this example to the forefront for you to look at is that clearly a line fit would not do very well with this. A line fit, this isn't a line. It's not a parabola. It's some kind of shape that comes up and down. In fact, it looks a lot like a bump. Well, a kind of function that you might plot like a bump is, let me show you what a bump function might look like. It's basically take something like a Gaussian, right? So let's define x goes from -3, steps of 0.1 to 3, and y will be something like a Gaussian of height 1 times negative squared. Oh, let's call this x2 actually. x2 and x2 squared, and we're going to plot, and I'll call this y2. Hold on, and we're going to plot x2, y2, plot it in magenta line. Okay. Oh, see that's a Gaussian. The Gaussian is like a little bump. And you can see it actually kind of is representing the data, not too badly. Obviously, the height isn't quite right, but that could easily be fixed by like saying, hey, how about making this something like 2? You say, there, okay, not bad. But really what I want is I want to fit this thing with the Gaussian, but I want the best fit possible. So what you see right here is I actually got pretty close just by doing this by hand. I picked 2 for the height, but really, generically, what I want to do is specify an A there and a B there. That's it. I want to pick the A and B that give me the best fit to that data in a least square sense. The problem is, just as before, when I showed you what happens with some nonlinear function, you get a nonlinear set of equations to solve for A and B. So how do you do it? Well, Matlab has an optimization routine built in. It's based upon iteration. And in fact, we're going to talk a lot about optimization next week. So next week is all about optimization. And you're going to get your first optimization routine right now, which is called FMIN Search. As the name implies, FMIN Search. F is the function. Min search is looking for the minimum of a function. So what are we looking for the minimum here? We're looking for the minimum error. And what we want to do is match it to this Gaussian somehow. So let's put this in, oops, edit, undo. Let's block that out for a minute, and let's say, look, what we want to do is take this xy data, and we want to just do this Gaussian fit to it. So what I'm going to do is I want these coefficients. And I want these coefficients to come out, which are going to be from this FMIN search command. And I want to do a Gaussian fit, so it's going to call a function called Gauss fit. And what I'm going to send in is initial guesses to what A and B are going to be. You know, let's pick A was 1, B is 1. Those are going to be my initial guesses. So let's send in A and B. And what I want to do is have this thing, with that initial guess, iterate towards the solution that's going to give me the least square error. Okay? Now, we're going to talk about how it might actually do this next week. But right now, we're going to just implement this FMIN search, because we're going to do curve fitting. And curve fitting is all about minimizing the error of your curve to the actual data. All right. So what this is going to do here is going to run this FMIN search command, and it's going to call GaussFit.m. It's going to look for a function called that. So file, new M file. Okay? And the way we would do this is make a function call, function. And what we want to do is basically Gauss fit, right? That's what we called it. Yeah, Gauss fit. Good. Gauss fit. And we're sending it some vector, let's call it x0, with A and B in it. In fact, maybe the first thing we do is say A is equal to the first component of x naught, B is equal to the second component of x naught. And what we want to evaluate is the error. Okay? So what we want to do is compute this error. We want to update the values of A and B. We started off with guesses of 1 and 1. And what this is going to do is iterate towards finding the best A and B possible, which minimizes the error. Well, what is the error? Well, so first of all, I have to basically have my data in here. So let's go ahead and copy it and paste it over here. I could also load it in or send it over if I'd like. So what I want to do is have my data there. And what I want to do with this now is say, OK, what am I trying to minimize? I'm trying to minimize this error. What is the error? Well, I'm trying to figure out how to minimize the absolute value, sort of the square of the difference between the two things. So, right? So if you remember, we square, we're going to take the function we want, which is a minus b times x squared. That's the function we want to fit it to, minus y. And we want to square that. That is what we're trying to minimize. We're trying to minimize the sum of this, right? So if you remember the least square fit error, you take the sum of the squares. So there, right there, is the sum of the errors. So what happens here is I have my x and y, here they are. I have A and B I sent in as 1 and 1. And what's going to happen in this routine, what FMIN Search does, it tries to iterate and changes the values of A and B every single iteration to try to move you towards the best A and B possible. So let's go and file save this. Save as. OK, GaussFit.m. Save. And now we can come back over here. And let's go ahead and run this thing. And once we run it, I'm going to get back here in this coef new values of A and B. So my new value of A is going to be coef first component of that. New value of B is going to be second component of that. And so now I can plot this here, this new y2. And let's just plot it and see what the results look like. And in fact, actually, let's go ahead and have it spit out what the values of A and B are. So if I run it, OK, wow, ran on the first try. You see this here? That is the least square fit Gaussian to that data. And the values of A and B, what's that called? I got to put, sorry, I got to put that there, semicolon there. Boom, run it again, there it is. Here are the values of A and B. A is 1.8733, B is 0.9344. So my guesses of 2 and 1 weren't too bad, but these are, in fact, the optimal guesses. So you can see this is a really awesome tool. FMIN Search, you give it a guess, and it tries to find it for you. By the way, the guess is very important. We'll find this out later, but the guess is tremendously important in practice. If you do not have a good guess on more complicated cases, you'll get not a very good solution. Here's the point about nonlinear systems. How many solutions do you know you have? There are no guarantees. You might have 1, you might have 5, you might have infinity. The problem with nonlinear systems is you don't know. So the problem is here, when you try to solve this, you're trying to give it a guess that looks at least reasonable, so the hope is that it converges to the solution that you're looking for. Converges to the global minimum. But FMIN Search can also get stuck in local minima, which are not the things you want. So just remember that FMIN Search isn't always going to work, and it's going to be determined a lot about what kind of guesser you are. Okay, so it's sometimes good to be a good guesser. So that's one thing. The other thing I want to show you in accessing this is if we look at the FMIN Search command, help FMIN Search. You know, here's how it generically works right there. X equals FMIN Search. You send it a function, or you tell it what function to send it. You send in your initial guess. That's one way. Now, if you want to do more interesting things, you can send in some options. So options include remember this is an iterative structure, so it's going to try to iterate to the best solution and it has some default tolerance. Well, if you want to change the default tolerance, you'd put in some options. Okay? So that's what it's saved for. Now the rest is you can actually have it give you a flag here, give you back some stuff about whether it converged or not. But what I'm going to suggest is I want to use this and send in that x and y. So this third slot is reserved for options. If I don't want to put any options in, I put blank boxes like that, and now I want to send in x and y. Okay? So the idea is you call the function and you send in these things. You send in options. If you're not going to do any options, you leave it blank like that with a blank vector expression, and then you send in the things you want, x and y. And in here now you have to, let's go ahead and comment these out so that they can't be seen anymore. And in here you say, well, I send in an x naught, some options, let's call them options, and then I'm sending in x and y. So I'm going to save this. Let's see if it works. Now you run it. Oop. Yeah, okay, I think actually you don't even have to put this in. If you have options, you just send in x and y. I think this will work. Let's see. Go. There. Okay. There you go. So what we've done now is some nice fancy things. We've done a nonlinear curve fitting. This is what FMIN Search is good for. And by the way, I would encourage you to become very good with FMIN Search. It's an extremely powerful, simple optimization tool which you can just access. And you can see what it does. We're obviously doing curve fitting with it, but really what else, it's just doing an optimization problem. You tell me what you want to minimize, it will go do it for you. That's it. And in our case, we're trying to minimize an error so that I can do a nice data fit. So there you go. FMIN Search, very powerful. And as you see, the way we've set it up here is you can pass variables in. But remember, do not leave this options out. If you leave that options out, it will complain. So the way to find out if you have options or not is you always go to the help thing. You say help, FMIN Search, and it tells you. Right there, it says, okay, look, here's how it works. You send it in. Here's the generic way, or you can send it in with options. And by the way, it doesn't tell you anything else to send back here. So once you've done what the defaults or what the FMIN Search allowables are here, now you can add variables that you want to pass in. Okay? And what we did here is we passed in the x and y, so that way in the right-hand side, we didn't have to have them at all. So these could be just gone altogether, and you don't need them. And so you just say, boom, there it is. You run, you get this beautiful curve fit. Okay, so let's finish off here, come up to the front. So what you've seen here is now a demonstration of all these curve fitting techniques between things that try to do a least square fit, things that go through all the data points, things like splines, which are really quite nice, right? Splining is really nice if you want to smooth data out. Remember, the spline doesn't give you a nice little formula for the trend, right? So if you do a line fit, what you get is y equals ax plus b, and it gives you the a and the b's. The spline is something complicated, but gives you a very nice result. And with FMIN Search, I gave you something you can do nonlinear curve fitting with. And that's going to be very important. You're going to have homeworks on that. So I want you to get to know FMIN Search very well. All of this curve fitting ultimately comes down to doing optimization. What we were trying to do is minimize the error. So next week, what we're going to talk about is optimization the entire time. So the idea is to have some lectures about how do you think about formulating an optimization problem, what are some of the methods that you use to, for instance, execute FMIN Search. So that will be up next.